Good afternoon, and welcome to Lecture 4 of College Mathematics, Math 208. Today we're going to be covering Section 4.4 from the book College Mathematics, Basic Operations of Matrices. We've got a few goals for today, and I'm going to do a couple things here. We'll keep my screen on for the time being, and then we'll turn that off. We've got a few goals for today. We're going to learn how to add and subtract matrices. Multiply a matrix by a scalar, calculate the matrix product of a row vector and a column vector, determine if the matrix product exists and what its dimension is, and then calculate the matrix product and understand that a matrix A times B is not equivalent to B times A. So I'm going to do a couple things right now. I'm going to turn off video capture for me. There we go. Okay. So first off, in my examples, I'm going to be using a couple of matrices, and I copied these matrices down as well. So this is the same set of matrices. Is my zoom proper on this? I'm just going to double check that with an autofocus. And then in the meantime, so we've got a number of matrices, and recall that a matrix dimension or size is determined by the number of rows and then by the number of columns. So an m by m matrix. So we're going to assume that we have a variety of matrices. These are A, B, C, D, E, and F as given. And we're going to start by talking about some basic properties. So, equality. So one matrix is equal to another. They're equivalent to each other if they have the same dimension, so they're the exact same size. So if it's a 1 by 2 matrix, they both have to be 1 by 2 matrices, etc. And if, and only if, every A value, so A is equal to U, and this is what we're indicating here. So each corresponding element has to be equivalent. So A has to equal A, B has to equal V, C, W, etc. It's kind of a relatively straightforward concept. Basically, if they look like each other, pretty much exactly, you have equality. Now we're going to talk about addition and subtraction of matrices. Two matrices can be added and subtracted from each other, or to each other. In order to do this operation, they have to have the same dimension. They have to have the same size. If they do not have the same size, you cannot add them together or subtract them. So, let me quickly change which marker I'm using. I noticed I was using the wrong one. Anyways, so they have to have the same size, the same dimension, exactly. If they do not, the operation is not defined. If it is defined, then we basically do the operation element-wise. So, meaning we take element-wise, meaning A1, 1 plus B1, 1. A22 plus, I'm sorry, A22 plus B22 goes to this position. So it goes element-wise, piece by piece by piece. And we'll do some examples in just a little bit. What you'll recall, or what you'll notice, matrices are also commutative. In other words, the order in which you add them does not matter, and associative. So if you can add matrix 1 to matrix 2, and then add matrix 3, which is what we're indicating in this, the order doesn't matter. So you can do x plus y together, and then z, or y plus z, and then x. You'll get the same result. Let's do a couple of examples. And we're going to use the matrices that we have here. So when we say this, we say A, B, C, D, etc. So we have A and B, and that's indicated by the two matrices that are shown, which is 1, 2, 3, minus 4, 0, 6. We do the operation element-wise, which means 1 minus 4, 2 minus 0, 3 minus 6. And that equals minus 3, 2, and minus 3. We just step through the operation element-wise. A plus C. The next operation that we're going to try and do is A plus C, which is A, which is a 3 by 1 matrix, and C, which is a 1 by 3 matrix. They are not the same size. Because they are not the same size, this operation is not defined. So a plus c does not exist. It's not a defined operation. D plus E. So D is a 2 by 3 matrix, and E is a 3 by 2 matrix. Again, they're not the same size. So this operation, again, is not defined. This time we're going to do E plus F. This operation is defined. They are both 3 by 2 matrices. So let's go ahead and do that. And this is E plus F. I'm going to quickly write them out. 2, 1, 3, 1, 2, 4. Remember, we do the terms element-wise. We're going to end up with a 3 by 2 matrix. So 2 plus 3, 1 plus 4, 3 plus 2, and that's our first column. And then 1 plus 3, 2 plus 1, and 4 plus 0. And that equals 5, 5, 3 plus 2 is 5, 4, 3, and 4. So this is the result of adding, sorry, let me move that over just a little bit, I apologize. So this is a result for adding those two matrices, E and F, together. A zero matrix and an additive inverse. So a zero matrix is the equivalent of 0. When we're counting on numbers, we have 0, and if you add 0 to any number, you still end up with that number. The same thing is true for matrices. And a zero matrix is any matrix that is literally all zeros. And that can come in many forms. Usually we just denote it by 0. And remember, it's a matrix, it's not a number. But it could be 0, 0, 0, 0, 0, 0. So this is a 3 by 2 matrix, but we'll just designate it with 0. So if we're doing any operations with it, we would do A plus 0. Even though A is a whatever dimension matrix, you can still do that operation. Any matrix plus a 0 matrix is equal to the A matrix. Multiplied by a 0 matrix is equal to 0. And for addition, the 0 matrix has to be the same dimension as A. Generally speaking, we assume that it is, but that is not always the case. So there are some cases where that would not occur. The additive inverse is the matrix that you add to another matrix in order to get the result matrix 0. It sounds very confusing. It's really not. If you think of it in terms of numbers, the additive inverse of the number 3 is minus 3, and that gives you 0. So this is in terms of numbers. The additive inverse of the number minus 6 is 6, because this gives you 0. This is the same type of result in matrices. We just call it an additive inverse, and it's the negative of the matrix that we start with. It's a pretty straightforward approach. I mentioned examples of matrices. That's what we're indicating right here. Zeros in every element is equal to 0. It can be whatever dimension that you need it to be. Scalar multiplication. You can multiply. Scalar is a constant value. It's scalar is what we typically have been thinking of as being a number. So 5 is a number, a scalar. 3 is a scalar. Minus 10 is a scalar. It's generally what we've always been calling a number. Now we're going to call it a scalar because we're using it with matrices, and we call it scalar multiplication. And this is a very, very straightforward application. You multiply a matrix, and recall that we're using these matrices to begin with. So 4 times A is 4 times 1, which is 4, 4 times 2, which is 8, and 4 times 3, which is 12. And if we're doing 1/2 times C, and C is this 4, 5, 6 matrix, again, we do it element-wise, so 1/2 times minus 1/2. Wow, I might have a misprint somewhere. I'm thinking that my intent was this should be a minus, so we're going to make this a minus. So we have minus 1/2 times C, so minus 1/2 times 4 is minus 2, minus 5/2, and minus 3. I think most of these are pretty straightforward applications, and we're not really going to have too much misunderstanding of what that means. Since what we've covered so far is in this section now allows us to work with something we call a matrix equation. So you can basically set up equations using matrices. So we know that from equality, a matrix is equal to another matrix if and only if the elements themselves are equal to each other and they're the same dimension. So now we're going to look at a matrix equation, and we know that when we multiply this by 2, we're going to end up with a 2 by 2 matrix. When we add that to this, we're going to end up with a 2 by 2 matrix. And that can be equal to another 2 by 2 matrix. So let's set up the equation and see what happens when we do this. So we have WXYZ plus 2 times 1, 2 minus 2, 3, 4, 16 minus 8 minus 2. The first thing I'm going to do is I'm going to add multiply through by the scalar. It's the easiest operation to do. So I'm going to do 2, 4 minus 4, 6. And I'll just bring this down. So now we have W. Remember, addition is done element-wise. So now we have W plus 2, X plus 4, and I'm working with these two, this one and this one, Y minus 4, and Z plus 6. And that equals 4 minus 8, 16, and minus 2. And we're saying, well, how can they equal each other? They will equal each other if each term is equal to each other. By saying that, what we're saying is that W plus 2 is equal to 4, that excuse me, X plus 4 is equal to minus 8. Remember, element-wise, this goes to this one goes to this one goes to this. So Y minus 4 equals 16, and Z plus 6 is equal to minus 2. And then we just solve for our unknowns. In this case, we have W equals 2, X equals minus 12, Y equals 20, and Z equals minus 8. We'll cover matrix product, etc. in the next lecture. Thank you much.